Understanding deep learning models like CNN that can accurately identify objects in images or classify images into different categories is an important skill to learn for AI and machine learning job roles. And in today's video, we will break down the fundamentals of convolutional neural networks or CNNs, an essential deep learning algorithm designed for image classification, object detection, and segmentation. We will cover everything from the convolution layer to feature extraction and classification, and show you how CNNs power tasks like facial recognition and medical imaging. And if you're looking to take your skills to the next level, don't forget to check out our free masterclass on AI, machine learning, Agentic AI, and data science. This masterclass is perfect for IT professionals looking to fast-track their career in the AI and machine learning fields. The link is right in the description and pinned comments. Also, this video is part of our AIML track job-oriented program where professionals like Utkarsh, Shrija, Debashish, Roshan, and many others have successfully landed high-paying jobs and top certifications in AI. So let's dive into the video.
So the convolution neural network is a deep learning algorithm specifically designed for any task where object recognition is crucial, such as image classification, detection, and segmentation. Okay. Now, suppose this one is the convolution neural network. Okay. And our task is to classify some particular image, okay, into some class. So here you can see that we are having some the input, okay, and in that input we are having the image. After that, there is a series of different layers that are present here, okay. Some are used for the feature extraction and some are used for the classification, okay. Now the main layer over here is the convolution layer, the fully connected layer, okay, and the pooling layer. Now what happens in case of the convolution layer? We apply some kernels to it, okay. So the kernel is nothing but the filter, okay. Now after applying the filter to it, uh, we get some output from it, okay, and we fit that output with the ReLU activation function. After that, we do some feature extraction with the help of pooling layer, okay. Now after that, the same operation is performed, like we have multiple convolution layers, okay. In that we use some kernels, then we apply the ReLU activation function, and after that we apply the pooling layer, okay. So this architecture we need to design, okay, in order to get a substantial information from the input, okay. After that, we form a flattened layer, okay, a flattened layer, because from here we are performing the classification task, okay. So before this, this is the convolution layer where only we are our task is to reduce the information, and we just need to focus on some important features, okay, of some images, okay. And this flattened layer here, it will become the input layer for the neural network, okay. Now here you can see for the classification task we are having fully connected neural network, okay, and in that fully connected neural network we are having the same structure that we have discussed in the artificial neural network, okay. So we have the input layer, then the hidden layers, and the output layer there, okay. And in the output layer we'll get some probabilities for different classes. The class which has the maximum probability, that will be our final prediction, okay. For that we will be using the argmax, right. And for that we will be using some numpy arrays, okay. So in this way this convolution neural network work, okay. So there are certain building blocks of this convolution neural network. So from here only you can see that there is the convolution layer, right? So this convolution layer applies a filter or kernel, small matrix like 3 by 3 that slides over the input image, learns the local patterns like edges, corners, and textures, and its output is called as feature map or activation map. Okay, we'll see how this convolution operation is performed. Okay, now here the output will get from the convolution operation here. Okay, so we do some convolution operation between the images and the kernel. Okay, and we add some biases. After that we'll get the feature map. Okay, then there is activation function ReLU, that is very important. It adds non-linearity to help the complex patterns, as well as it is helpful when we got some negative values in the output. Okay, so we know that the ReLU activation function works in such a way that if the values become negative, then it will convert it into zero. Okay, and if these are positive, then those points will be considered. Okay, so in this way, ReLU activation function work there. There is one more layer called pooling layer. Okay, so in that we will be having max pooling or the average pooling. So this max pooling or average pooling, it is used for the downsampling the feature map. Okay, so it is like a if you just want to consider the important features, then pooling layer it is used. Okay, we'll see how it will work. Then we are having flatten layer. So whatever may be the output of these convolution network, okay, that will be converted into a single flatten layer, and that flatten layer will become the input for the dense layer or fully connected layer. Okay, so here the fully connected layer, it is used for the classification purpose. Okay, so these kind of structure is present for the convolution neural network. Okay, now what are the applications of the convolution neural network? So you can say that a convolution neural network is the base for all the applications that are used for the image classification, object detection, image segmentation, facial recognition, video analysis, okay, medical imaging, OCR, recommendation system. Okay, so if you want to do some classification task, like if the particular object is like a here, it is cat or dog, right? So in that case, you can use the convolution neural network. If you want to identify where the object is located along with the classification. Okay, now, if you want to do different object detection, like here in this image, you can understand that this is a cat, this one is dog, and this one is duck, right? Similar to here, this one is car, this is dog, this is horse, right? This is person, right? So this kind of image class detection, if you want to do object detection task, if you want to perform, okay, for that purpose you are using the convolution neural network. Similarly, like in the medical field, suppose if you want to identify the cancerous tumor, whether it is a tumor or not, right? So here you can see these are the X-rays, okay, scans of the brain, where the image detection task, or the you can say the tumor detection task is performed. So here from this pattern, the CNN easily understand that the tumor is present in the brain, right? Similar to that, facial recognition task for the security purpose, okay, for the aerial image processing, satellite image processing, okay. So there are so many applications of these convolution neural network, okay, and every application, or you can say all the processes which are used in this task, for that the CNN architecture is the base, okay. Based on the CNN, every other architecture has been built, okay. So we'll see what are different components of the CNN architecture, okay. So from here you can see that we are having the convolution layer there, right? So in the convolution, what we do, we apply filter, okay, and filter that is also called as kernel, Okay, so how this kernel and the filter work, we'll see there. Okay, so suppose if we are having some image, okay, in Python, the images are considered as the arrays of the numbers. Okay, so suppose if we are having some image like 6 by 6 image, so the 6 is the height and the 6 is the width. Okay, so this is the grayscale image. Okay, two-dimensional grayscale image. So when we start the convolution operation there, okay, so we need to consider some size of the filter. Okay, so mostly the filter size that we consider is 3 by 3 or 5 by 5 or 7 by 7. Okay, most of the time these filter sizes are considered. Okay, now you are free to use any other sizes as well. Okay, but mostly the preferable sizes are 3 by 3, 5 by 5 and 7 by 7. Okay, now suppose we are considering a filter with size 3 right here. Okay, and in that the values are randomly assigned values. Okay, so these values are assigned by the our network. Okay, and these are like randomly created values. Okay, you can consider these values like a weights. Okay, these values are like a weights. Okay, now here first what it will do, it will consider the first 3 by 3 matrix there. Okay, so suppose this is the point, right? So 1 2 and 3, 1 2 and 3. Okay, so this 3 by 3 matrix is considered for the convolution operation. Okay, now what happens in the convolution operation, it will do some multiplication, row wise multiplication operation and the addition operation. Okay, so what it will do, it will consider first row, like 4 is multiplied by 1. Okay, then it is added to 9 multiplied by 0, then it is added to 2 multiplied by -1. Okay, so this entire convolution for the first row is completed. Then it will move down, and the 5 multiplied by 1 plus 6 multiplied by 0 plus 2 multiplied by -1. Okay, then it will shift down, then 2 multiplied by 1, then 4 multiplied by 0, then 5 multiplied by -1. Okay, so in this way this calculation is performed like this. Okay, in this way this calculation is performed. So all the multiplication operation and the addition operation for each and every you can say the pixel points is completed, and we got the final one integer, right? And that is placed inside this result. Okay, this result here it is called as feature map. This result here it is called as feature map. Okay, now we need to decide the size of that feature map. Okay, we need to decide the size of the feature map here. Okay, now in order to calculate the size of the feature map, we are having this formula. Okay, so the output width for the feature map, that will be calculated like nw minus kw plus 2p divided by s plus 1. Okay, and similarly the output height is calculated as nh minus kh plus 2p divided by s plus 1. Okay, now from what are these nw? Okay, so here you can see this nw is nothing but the width of that image, and nh is nothing but the height of that image. Okay, in that if we consider the width size, okay, then we need to consider the kernel width size. Okay, so here as well for this kernel we are having this kw and kh. Okay, so kw is nothing but the width of the kernel and kh is nothing but the height of the kernel. Okay, so from the width of the image we subtract the width of the kernel plus 2p. 2p here, p is nothing but the padding. Okay, p is nothing but the padding. Now here we are considering that padding is equal to 0 and stride is equal to 1. Okay, so s here it is the stride. Okay, we'll see in what is the padding and the stride. Okay, so for now you consider that stride is equal to 1 and the padding is equal to 0, and in that we'll add the 1. Okay, so we'll be getting the value of this particular, you can say, the feature map. Okay, so here you can see that we are having this 6 by 6 image. Okay, so if you put that value in this formula, so it is 6 minus 3 plus padding is 0, therefore it is 0, and divided by 1, right? So 6 minus 3, it is 3. 3 divided by 1 is 3. 3 plus 1, it is 4. So here you can see the size is 1, 2, 3, and 4. Okay, similarly for this, here we are having nh is 6 and the filter size is 3, right? So same operation will be performed, like 6 minus 3 plus 0 divided by 1 plus 1. So the height of that particular feature map, sorry, height here, it will be the 4, right? So previously I told you about the width, sorry. So here height and the width both are 4 by 4, right? So the value of this is 4 and this is 4. So the feature map size will be the 4 by 4. Okay, now in that 4 by 4 matrix, one by one, what it will do, it will calculate the values, okay, and put it in that, right? So here you can see, after the calculation, because of this stride 1, okay, so this square will be shifted on the right hand side, okay, on the right hand side like this, okay, and after that the next value is calculated on the same filter. Okay, again here 9 will be multiplied by 1. Here you can see 9 multiplied by 1, 2 multiplied by 0, and the 5 multiplied by minus 1. Okay, so the similar kind of convolution operation is performed after multiplication and addition, or you can say the convolution operation. The second value is calculated and that will be placed over here. Okay, again after that it will be shifted like this. Okay, now here it will be shifted like this. After that it will be shifted like this. Okay, so the 4 times it is shifting because there are 4 values that we need to calculate, right? So after shifting, there is no like there is an end of that particular shifting. So what it will do, it will shift down. Okay, it will shift down there, 3 by 3 matrix. Okay, and again it will calculate the values with this filter. Okay, and these values will be like placed over here. Okay, so in single convolution operation, all those multiplication addition operation is performed and all those values are placed over here. Okay, so in this way it will create the first feature map. Okay, so the question is, what is the purpose of k? K is nothing but, you can say, the kernel height, okay, and kernel width. Here you can see the width and height of the kernel. The explanation here you can see the kernel height and the kernel width. Okay, you can consider this as k. Instead of f, you can consider k. K is the kernel, okay, filter. Filter, it is used in order to perform the convolution operation. So here it is k size, right, and here is the k. You can consider this as a k. Okay, so kw and kh is nothing but the width and the height of the kernel. Okay, so after calculation, okay, after calculation, here you can see this is, you can say, the calculation for the feature map. Okay, this is the calculation for the feature map. Okay, now that will be calculated over here. Okay, so this first, you can say, the kernel operation is formed. Now yes, so this first convolution operation is performed. Okay, now we'll discuss about this stride. Okay, we'll discuss about this stride there. Now here, if you want to like reduce the, you can say, the images. Okay, so for that purpose we are having the padding and the stride option there. Okay, padding and the stride option there. Now here you can see, when we use padding is equal to 0, when we use padding is equal to 0, so in that case the feature map that we obtain over here, it is smaller than the input size. Okay, so here uh, uh, in the beginning we are having the size of the image as 6 by 6. Okay, now after applying the filter with padding equal to 0, we got the feature map of 4 by 4. We got the feature map of the 4 by 4. Okay, now because of this, what happens here, it will reduce the size of the image. It will reduce the size of the image. Okay, now if you want to if you want the same size feature map, okay, so for that purpose you need to add some padding there. Okay, you need to add some padding there. Okay, so here you can see we have added one padding. Okay, and that padding is nothing but the zeros. Okay, so a layer, or you can say the a boundary of the zero are added around this image. Okay, so this is the actual image pixels, okay, that are like highlighted in the orange. And when we use padding equal to 1, okay, when we use padding equal to 1, because of that what happens, we got the image. Okay, we got the image which is equal in the size. Okay, so how this will happen, okay, so I will tell you. Okay, so here you can see we are having this formula there. Okay, we are having this formula that nw minus kw plus 2p. Okay, now suppose if we use p equal to 1 there. Okay, if we use p equal to 1, p equal to 1, so because of that what happens, so it will become like 6 minus 3 plus 2 divided by 1 plus 1. Okay, so what is the output? So it will give 3, right? 3 plus 2, 5, 5 plus 1, 6, right? So here the output will be 6. Similarly for the height, right? So it will be like 6 minus 3 plus 2 divided by 1 plus 1. It will give you the value 6, right? So if you want to have the same size of that particular feature map that you are obtaining after the convolution operation. So for that purpose, what you will do, you will be using p equal to 1. You will be using p equal to 1. Okay. Now, if you want to, you can say extract only the high level features. Okay, if you only want to extract the high level features from your image, okay, and that will be calculated in the feature map. Okay, so for that purpose you need to use the stride. Okay, the larger value of the stride. Okay, larger value of the stride. Now here you can see we are having this original image as 6 by 6. Okay, and here we are using this stride equal to 2. Okay, what is the stride? Stride is nothing but the sliding operation. Okay, you can say sliding operation. When we are having s equal to 1, so it will slide by one row or one column at a time. Okay, so suppose if this is the image over here. Okay, this is the image over here. So originally, the first convolution operation is performed from the first 3 by 3 arrays. Okay. After that, when we use this stride equal to 2, what it will do? It will shift our box by 2 like this. Okay. Now, after shifting the box, it will calculate the second value. Okay. Now, if you try to shift our box by 2 here, so here you can see we are going outside the image. So this is not possible. So what it will do? It will shift the 2 boxes downside. Okay, like this. Okay. Now, after that, it will calculate the values. After that, it will shift by 2 boxes. Okay, then again it will try to shift by 2 boxes, so it will go outside. Now below that, again it will shift by two boxes. Okay, so here it is going outside. Okay, so because of this stride equal to 2, what will happen over here, our feature map that will be reduced. Okay, now here only you can say the important features are, or the high level features are extracted. Okay, only the high level features are extracted over here. Now, if you want to keep your image, or you can say the feature map similar to your input image, you need to use padding equal to 1. Okay, and stride equal to 1. If you want to reduce or only extract the high level features, in that case, you need to increase the size of the stride. Okay, size of the stride. Yes, when we use the stride, okay, equal to 2, so in that case, what happens? It will be like reduce the image, okay, and we will be getting only the important features. Okay, we will be getting only the important features. Okay, but if you want to preserve all the characteristics of the images, in that case you need to use stride equal to 1 and padding equal to 1. Okay, so most of the time, suppose if you are having some image like 1920 by 1080, right? So here you can see we will be having very large, you can say, the matrix there. Okay, now from this matrix of the image, okay, so this is like HD image, right? This is the HD image. Now from this HD image, suppose if you want to extract only the meaningful information, and if you want to reduce the calculation there, okay, so in order to perform that operation, you need to use or consider the size of the stride. Okay, because what happens whenever we are having larger number of images, okay, so for that we will be having you can say the more number of trainable parameters. Okay, so in order to reduce those trainable parameters, okay, so if we consider like if we are having grayscale image, okay, like this, okay, 1920 by 1080, so after you can say feeding to the neural network, you can see that we can have the trainable parameter like the multiplication of these, right? So if we just do the calculation, like, okay, if we just do the calculation between like 1920 multiplied by 1080 there. Okay, so these many you can say the trainable parameters will be there. Okay, like it is 20,073,600, and if it is the three-dimensional image, okay, like if it is a colored image, in that case 62,020,800 trainable parameters will be created. Okay, now based on the image size, we consider the size of this particular sprite and the padding. Okay, so for the padding and the size, we if the images is smaller, okay, so for that case we can consider s equal to 1, and if the image is larger, then in that case we can consider s equal to 2. Okay, because it is shrinking, because in the first stage only it is shrinking the image down, right? But when we consider that we are having multiple convolution layers that are available for the feature extraction, okay, so in that case uh, uh, we if we use the larger value of the stride, then we will be getting very smaller fraction of the images, and it may happen that the you can say the features are eliminated, or useful features will be eliminated, and we cannot do the correct classification. Okay, so you need to be careful while selecting the values of the paddings and the strides. Okay, now this is about the convolution on the black and white image or grayscale images. Suppose if you are having the color images, okay, so where we are having the three channels, okay, where we are having the three channels, so the channels are the RGB channels. The channels are the RGB channels. Okay, R, G, and B. Okay, RGB channels. So what is this RGB? R is red, right? Green and blue. Okay, red, green, and blue. So three channels will be present, and all these three channels will be made up of the two-dimensional arrays. Okay, so here you can see if you are having some color image. Okay, so in that colored image, we will be having three channels. Okay, like this is for the red, this is for the green, and this one is for the blue. Okay, this is the RGB channel. Okay, now the size of that particular channel, single channel, is 6 by 6. And when we are having three channels, so we need to multiply it by 3. So okay, so because of this it will become the three-dimensional tensor. Okay, three-dimensional tensor. Okay, so every colored image is the three-dimensional tensor. Now if you want to apply the filter for that, okay, so you will be having the same channel filters. Okay, like there R, G, and B. Okay. So what will happen over here? So it will do the convolution operation between the red and the red. Okay. Then green and the green, and the blue and the blue. Okay. So we know that the output of every convolution is the single number. Okay. So here we will be getting the single number. After that, in the green we will be getting the single number, and in the blues we will be getting the single number. When we add all those numbers, okay, so we'll be getting a single number. Okay, so that will be reduced. Okay, that will be reduced, and because of this reduction, we'll get the feature map which is two-dimensional. Okay, which is two-dimensional. That is, we are you can say extracting the information from the three-dimensional channel and reducing that into a two-dimensional image. Okay, so this is the feature map. Okay, this one will be the feature map. Now if we are having, suppose, multiple filters, okay, so it is similar for the two-dimensional images or grayscale images as well. Okay, so suppose if you are having the filter 1 and the filter 2 like this. Okay, filter 1 and the filter 2 like this. Okay, so this filter we will be having some feature map 1. Okay, feature map 1, and for this second filter we will be having second feature map. Okay, feature map 2. Now this will be act as a two three-dimensional, you can say, the channels. Okay, so here this is the free feature map for the first filter, and this one will be the feature map for the second filter. Okay, so in this way, if we increase the sizes of the filter, because of that what will happen, so in this we will be getting the multiple you can say the outputs in the feature map. Okay, now the number of feature maps that we are getting over here will be equal to the number of filters. Okay, so here you can see the number of feature map is equal to number of filters. Okay, number of filters. So how many numbers if you are using, like 30, 60, so for that you will be getting the 60 feature maps. Okay, 60 feature map. Okay, now this is the convolution operation. Now what happens sometimes, some like the values that are calculated inside over here will be the negative values, like sometimes it will be calculating like -1. Okay, but the range of the color, okay, a pixel is varying from 0 to 255, that we have seen, right? 0 is for the black and 255 is for the white. Okay, and all other values that falls between these 0 to 255 are in the spectrum of the gray, right? So the grayscale values will be there. Now sometimes what happens, because of this calculation, because of this calculation of the convolution, we will be getting some negative values. Okay, so in order to avoid these negative values, we are having this ReLU activation function. We are having the ReLU activation function. So what we'll do, we'll apply the ReLU activation function on this feature map. Okay, and we add some bias value as well. Okay, so this bias value will be added to this one and this one as well. Okay, so if we add if we perform this ReLU activation function over there, so we know the output of the ReLU is max of 0 or x, right? So if the values are negative, okay, so suppose this is the x-axis, okay, this is the x-axis and this one is the y-axis. Okay, if the values are 0, then that sorry, negative, then this will become directly what, 0. Okay, so this is the 0 value, suppose. So if the value of x is negative, okay, so that will be straightforward 0. Okay, that will be straightforward 0. Okay, so in this way there will be no chances of the pixel value becoming 0 negatives. Okay, because of this ReLU activation function. ReLU activation functions will convert the negative values to 0. Okay, if it is positive, then that will remain as it is. Okay, if the values are positive, then that will remain as it is. So in order to avoid that negative values, we will be applying this ReLU activation function there. Okay, now what happens, our task is different at different you can say the project. Okay, we will be having different tasks at different you can say the, because the why we are avoiding the negative values, because we are having the values of the color pixel varying from 0 to 255. Okay, if the value become negative, so that will not be considered as a color value, right? Because 0 is for the black and 255 is for the white. Okay, if the value become negative, then it will not fall in the range between the 0 and 255. Okay, so for that purpose we will be using this ReLU activation function there. Okay, now we are having so many different you can say the tasks. Okay, so sometimes we need to extract the useful information. Okay, and sometimes our task is to the smooth the features. Okay, we need to uh, avoid the noises from the images. Okay, so for that purpose we are having this pooling layer. Okay, for that purpose we are having pooling layer. So there are two famous pooling layers. Okay, the max pooling and the average pooling. Max pooling and the average pooling. Now if you see over here, after applying the ReLU activation function, we are having this pooling layer in between all those you can say all those convolution layers. Okay, so when we are going to pass the information from one convolution layer to another convolution layer, we are using the pooling layer in between. Okay, so how this pooling layer work? So there are two types of pooling. One is max pooling and second is the average pooling. Okay, now what happens in our you can say the convolution operation, our model is try to extract the low level features, mid level features and the high level features. Okay, so suppose here it is like the face detection task. Okay, so in the low level feature what will it will extract? So it will extract the dark spots, right? So the places where the you can say the intensity of the color changes. Okay, the place where the intensity of the color changes, that point will be considered as the edges. Okay, that points will be considered as a edge. Okay, so that edge detection part will be considered under the low level feature. Okay, then if you want to extract the mid level features like eyes, nose, okay, from your face, then for that we are having the mid level feature extraction. And if you want to extract the complete information, okay, so for that we are having this facial or you can say the high level feature extraction. Okay, now in the max pooling what it will do, it will increase the intensity or you can say it will consider only the dominant points, okay, from the image, okay, from the image or the feature map, okay. So suppose this one is the feature map, okay, this one is the feature map where we are using the stride equal to 2, where we are using the stride equal to 2, okay. So first it will be considering this box, okay. Now in the max pooling what will happen, so whatever comes inside this box, okay, so it will be extracting the largest value, okay. So suppose here if you compare that this one is the 4 9 then 6 and the 5, the largest value is 9, okay. So what it will do, it will be like extracting 9 over here, okay. Similarly for the this box 2 5 2 4, so the 5 is the largest, so the 5 will be extracted, okay. Similarly for here if you see 6 is largest and for this box 8 is largest, okay. So the maximum value only be considered in the max pooling, maximum value will be considered during the max pooling, okay. Now in case of average pooling what will happen, in the average pooling what it will do, it will calculate the average of all those points, like here the average of 4 plus 9 plus 5 plus 6 divided by 4, okay, that will be 6. So that 6 will be considered over here, okay. Again here the average of those points like 2 plus 5 plus 2 plus 4 divided by 4, the average point is 3.3, okay. So because of this average pooling what will happen, it will give the effect of the smoothing, it will give the effect of the smoothing, okay. So it will convert the image into the smooth image, okay. And because of that what happens, suppose if there are some noise present in our data, if noise is present in our data, so that noise will be removed, okay. So it will be act as a noise removal, okay, it will be act as a noise removal, okay. But most of the time what happens in when we are doing some object detection task, so for that purpose we will be using the max pooling, okay. Now no max pooling consider only or it will emphasize the prominent features only, right, it will be emphasizing the prominent features only. Now it will be like it will be like very useful when we are having translation invariance, okay, when we are having the translation invariance, okay. So what is the translation invariance, so consider this image over here, okay, consider this image over here, this is the image of the cat, okay. Now when we consider this image as the numpy array over here, okay. Suppose this is the 4 by 4 image like this, okay. This is the 4 by 4 image like this, and here as well this one will be the 4 by 4 image, okay, 4 by 4 image. Now when we perform the training operation there, okay, when we perform the training operation there, because of the pixels, okay, or the patterns that is available for this particular you can say the images, okay. So it will it is very difficult to classify some particular objects, okay, because here you can see this 1 2 3 4 5 6, okay, these are not having any you can say the color variance, okay, over here, okay, there is no color variance over here, okay. The color variance is present only in these boxes, right, 1 2 3 4 5 6 and 7, right. So in these boxes only we are having this color variance. Now because of that what happens, our neural network become confused, okay, our neural network become confused. But when we perform or use this max pooling there, okay, since it is extracting the largest value only, okay, since it is extracting the largest value only, because of that what happens, even if we are having some you can say the translational invariance like this, okay, so the shifting in the position of particular object, or you can say if you are having S like this, we can also have S like this, right? We can also have S like this. Okay, so there are different, you can say, the structure of S can be present. So this is the mirror image of the S, right? So this is the horizontal image, this is the vertical image, right? So vertical orientation of that particular S. So all the S are the same, all the S are the same, and we as a human can easily identify that. But because of the pixel placement of those particular images, it is very difficult for our machine to understand. Okay, it is very difficult for our machine to understand where the exact location of the pixel is placed. Okay, so for that purpose as well, the max pooling is very useful. Okay, so it is like generally perform better in case of the translation invariance. Okay, now most of the time we are preferring this max pooling only. Okay, most of the time we are preferring this max pooling only, and we don't prefer this average pooling unless and until we are doing some smoothing task, okay, or the noise removal from the images. Okay, so here you can see we are having like the different leaf images. Okay, so this one is the leaf, and how this convolution neural network work. Okay, how this convolution neural network work over here. So here we are having the colorful image, like this is the green leaf. Okay, so the red, green and the blue channel is there, RGB image. Okay, so in this red we are having different, you can say, the values of our the image data. Okay, and here in the green we are having different values, and in the blue we are having different values. Okay, so first in the convolution layer. Okay, so when we see that what happens over there. Okay, so our kernel is applied. Okay, and it will slide like this. Okay, it will slide like this, and it will calculate the values of each and every, you can say, the data points like this. Okay, so suppose here it is a 3 by 3 kernel. When I slide over here, you can see the values are like changing. Okay, the values are changing. Okay, and it is calculating all those values. Okay, so suppose if I'm at this point. Okay, I'm at this point over here. Now what it will do over here, it will be multiplying the whatever may be the value that is available for this pixel. Okay, then it will do this multiplication addition operation, multiplication addition, and it will give the single value. Okay, so in this way it will be giving us the single points, right? It is giving the single points. Now here the you can say uh, padding value is equal, right? Because of this we will be getting the same values. Okay, now whatever you can say the values that you have considered in this convolution layers. Okay, so depending on that you will be getting the multiple values like this. Okay, so it is performing the uh, convolution operation, and it will be adding the bias over here. Okay, bias over here, and bias will be the randomly generated points. Okay, so it will be the single data point, and it will be added to all intermediate results and the biases. Okay, so whatever may be the values that we are considering over here, so after calculation the bias value will be added to the final result. Okay, now after that we will be passing that into the ReLU activation function. Okay, so in the ReLU activation function, what it will do, it will be like suppose if the negative value is calculated. So here you can see in this we are having this negative value, negative minus 0.8. So for that it will be considering 0. Okay, at this point. Okay, so wherever it is getting the negative values, like here if you see we are getting the negative value, and if you are having the positive value, suppose this is the positive value, right? 0.05. So that 0.05 value will be considered there. So wherever we are having the negative values, so ReLU activation function will discard those values, and that will be converted into the positive values. Okay, so if we see there that wherever we are having the negative values like this. Okay, so there we will be getting the positive sorry 0 values, and wherever we are having the positive values, so there we will be getting the maximum value whatever it is. Okay, so in this way this ReLU activation function will work, okay, over here. Now here if we apply this max pooling, okay, so here you can see for each and every, you can say the boxes, each and every boxes, it is just considering the maximum value, and because of that what will happen, it will be like giving the result, giving the result which is having only the you can say the dominant points, okay, dominant points. Okay, so suppose in this box if you see there that in the max box there are 0.6, then 0.46, 0.58 and 0.53 values were there. Now the maximum value is 0.6, so that 0.6 value will be considered. Okay, now because of this what happens, the size of the image will be reduced, okay, because of this max pooling. So here you can see the original feature map size was like 60, and because of this 2 by 2 matrix, the size of that particular you can say the output is reduced by 2. Okay, so as you increase the size of this max pooling, it will reduce the size of the final feature map. Okay, now after this combination of the max pooling and the feature map, here we will be having the outputs. Okay, like here it is just giving me this class 1, right, class 3. So how this calculation is performed, so after the max pooling it will be like flattened. Okay, so this is the flattened layer there. So there are like a 1690 neurons in this input layer, okay, for the dense layer. Okay, now here we will be having this calculation. Okay, so this softmax calculation, and everything is calculated wherever we are having, like here the maximum value is considered for this class 3. Okay, the maximum value is considered for the class 3. So after that we will be getting this you can say the a feature or the class which belong to the class 3. Okay, so in this way we this complete, you can say, the neural network work. Okay, so we are having first the input. Okay, we are having some inputs there, so that will be splitted into the particular channel. If you are having only the two-dimensional image, then that will be considered as single channel. Okay, now we pass that into the convolution layer. Okay, we'll consider the ReLU activation function for that convolution layer. Then we are having this max pooling. Okay, after that we are having this dense layer, and the output of the dense layer will be the class of that particular image.
So today we cover the concepts behind convolutional neural networks, from how convolution layers extract features to how the final classification is done. So whether it's image classification, object detection, or facial recognition, CNNs are crucial to the modern AI landscape. And remember, if you are looking to take your AI skills to the next level and fast-track your career, don't miss our free masterclass on the AI Track Job Program. Learn how to master deep learning techniques like CNNs and secure high-paying AI jobs. You can find the link to register in the description and pinned comments. Also, stay tuned for more informative videos on AI, machine learning, GenAI, and Agentic AI. Subscribe to our channel and hit the bell icon to never miss an update. So we'll see you in the next video.